The abstract factory design pattern is a creational design pattern that provides an interface for creating families of related or dependent objects without specifying their concrete classes. It represents a higher level of abstraction compared to the factory method pattern, as it focuses not just on creating a single object, but on producing a group of objects that are designed to work together. The main idea behind this pattern is to encapsulate a set of individual factories under a common interface, ensuring that all created objects belong to the same family and are compatible with each other. This is especially useful in systems where multiple product types must be used together consistently. In this pattern, an abstract factory interface is defined, which declares a set of methods for creating different types of objects. Each method corresponds to a product in the family. Concrete factories implement this interface and are responsible for creating specific variants of these products. For example, if the system supports multiple UI themes such as Windows and Mac OS, each theme will have its own factory that produces theme-specific components like buttons, checkboxes, and text fields. This ensures that all UI elements within a theme are consistent and follow the same design language. One of the most important characteristics of the abstract factory pattern is that it promotes the use of interfaces and abstractions rather than concrete implementations. The client code interacts only with the abstract factory and product interfaces, which makes it independent of the actual classes being instantiated. This level of abstraction allows developers to change or extend the system without modifying existing code, aligning perfectly with the open/closed principle of solid design. In .NET development, the abstract factory pattern is widely used in frameworks and enterprise applications where multiple related objects need to be created dynamically based on configuration or runtime conditions. For instance, database providers, UI frameworks, and service layers often rely on this pattern to manage object creation in a flexible and scalable way. Another key advantage of this pattern is that it enforces consistency across related objects. Since all objects are created by the same factory, there is no risk of mixing incompatible components. This is particularly important in large systems where different parts of the application must work together seamlessly. Overall, the abstract factory design pattern provides a structured and scalable approach to object creation, enabling developers to build flexible, maintainable, and consistent systems. The abstract factory pattern is essentially about creating entire families of related objects through a single unified interface, without exposing the details of their concrete implementations. Unlike simpler object creation approaches where objects are instantiated individually, this pattern ensures that a set of related objects is created together in a coordinated manner. The key concept is that these objects are not independent. They are designed to work together and therefore must be created in a consistent way. In practical terms, the pattern introduces an abstract factory interface that defines multiple methods, each responsible for creating a specific type of product. These products are typically represented by interfaces or abstract classes. For example, in a UI framework, the abstract factory might define methods such as createButton, createCheckbox, and createTextBox. Each of these methods returns an object that adheres to a corresponding interface, such as iButton or iCheckbox. Concrete factories implement this abstract factory interface and provide the actual logic for creating objects belonging to a specific family. For instance, a Windows factory would create Windows-style UI components, while a Mac factory would create Mac OS-style components. The important point is that each factory produces a complete set of related objects that are guaranteed to be compatible with each other. From the client's perspective, the process of object creation becomes much simpler. The client only needs to work with the abstract factory and product interfaces, without worrying about which concrete classes are being used. This eliminates the need for conditional logic and reduces dependencies on specific implementations. Another important aspect of the abstract factory pattern is that it improves code organization and readability. By centralizing the creation of related objects, the pattern avoids duplication and makes the system easier to understand. It also makes it easier to switch between different families of objects by simply changing the factory. In essence, the abstract factory pattern is about managing complexity in object creation by grouping related objects together and providing a consistent way to create them. It ensures that all parts of the system remain compatible and work together seamlessly, making it a powerful tool for building robust applications. The abstract factory pattern is most commonly used in scenarios where a system needs to create multiple families of related objects that must be used together in a consistent manner. It is particularly valuable in applications that need to support multiple configurations, environments, or themes, where each configuration requires its own set of related components. One of the most well-known use cases for this pattern is in user interface (UI) frameworks. Applications that run on multiple platforms such as Windows, macOS, and Linux often need to provide a consistent look and feel for each platform. Each platform has its own style for UI components like buttons, menus, and text fields. By using the abstract factory pattern, developers can create platform-specific factories that generate UI components matching the desired style. This ensures that all components within a platform are consistent and visually compatible. Another common use case is in database abstraction layers. Applications may need to support different database systems such as SQL Server, MySQL, or Oracle. Each database requires its own set of objects for connections, commands, and transactions. The abstract factory pattern allows developers to create database-specific factories that produce these objects, enabling the application to switch between databases without modifying the core logic. In .NET development, this pattern is frequently used in dependency injection frameworks and service providers, where different configurations require different sets of services. It is also used in enterprise applications where maintaining consistency across related components is critical. The pattern is also applicable in game development, where different environments or themes require different sets of objects, such as characters, weapons, and backgrounds. Each environment can have its own factory to ensure consistency. Additionally, the abstract factory pattern is useful in systems where object creation involves multiple interdependent components. By centralizing the creation logic, it ensures that all components are compatible and reduces the risk of errors. In summary, the abstract factory pattern is best used in complex systems that require the creation of multiple related objects in a consistent and controlled manner. The abstract factory pattern is used to address several challenges associated with object creation in complex systems, particularly when dealing with families of related objects. One of the primary reasons for using this pattern is to ensure consistency and compatibility among objects that are designed to work together. When objects are created independently, there is a risk of mixing incompatible components, which can lead to errors and unpredictable behavior. The abstract factory pattern eliminates this risk by ensuring that all objects are created through a single factory that enforces compatibility. Another important reason for using this pattern is to reduce tight coupling between the client code and concrete classes. By relying on abstract interfaces, the client becomes independent of specific implementations. This makes the system more flexible and easier to modify or extend. For example, if a new family of objects needs to be introduced, developers can simply create a new factory and corresponding classes without changing the existing code. The pattern also supports the open/closed principle, which is a key aspect of maintainable software design. By allowing new families of objects to be added without modifying existing code, the abstract factory pattern makes the system more robust and adaptable to change. In addition, the pattern improves code organization by centralizing object creation logic. This reduces duplication and makes the code easier to read and maintain. It also enhances testability, as the client code can be tested using mock factories and objects. Overall, the abstract factory pattern is used to build flexible, scalable, and maintainable systems that require consistent object creation. Without the abstract factory pattern, creating families of related objects often involves direct instantiation and complex conditional logic. Developers may write code that explicitly creates objects using concrete classes, leading to tight coupling and reduced flexibility. This approach becomes problematic as the system grows and new object families are introduced. For example, a developer might create UI components like this: var button equals new Windows button, var checkbox equals new Mac checkbox. This results in inconsistent and incompatible components being used together, which can cause issues in the application. With the abstract factory pattern, object creation is centralized and controlled. The client code uses a factory to create related objects: var factory equals new Windows factory, var button equals factory.create button, var checkbox equals factory.create checkbox. Now, all components belong to the same family, ensuring consistency and compatibility. This approach simplifies the code, reduces duplication, and makes it easier to switch between different families by changing the factory. It also improves maintainability and scalability. The abstract factory pattern is implemented by defining abstract product interfaces, concrete product classes, an abstract factory interface, and concrete factories. The abstract product interfaces define the structure of the objects to be created, while the concrete classes provide specific implementations. The abstract factory interface declares methods for creating each type of product. Concrete factories implement this interface and provide the logic for creating specific families of objects. The client code interacts only with the abstract factory and product interfaces, ensuring independence from concrete implementations. This structured approach ensures consistency, flexibility, and scalability in object creation. In the context of .NET development, the abstract factory design pattern is widely used in building scalable, maintainable, and platform-independent applications, especially when dealing with multiple related services or components that must work together. A practical real-time example can be seen in an enterprise-level application that supports multiple database providers such as SQL Server, MySQL, and PostgreSQL. Each database requires its own set of related objects, such as connections, commands, and transactions, and these objects must be compatible with each other. Instead of tightly coupling the application logic to specific database implementations, the abstract factory pattern provides a clean and extensible way to manage these variations. In such a system, developers define an abstract factory interface, for example iDatabase Factory, which includes methods like createConnection, createCommand, and createTransaction. These methods represent a family of related objects required to interact with a database. Then, concrete factory classes such as SQL Server Factory, MySQL Factory, and PostgreSQL Factory implement this interface and provide database-specific implementations. For instance, SQL Server Factory will return SQL Connection, SQL Command, and SQL Transaction, while MySQL Factory will return corresponding MySQL-specific objects. When the application starts, it determines which database to use based on configuration settings, for example, from appsettings.json in ASP.NET Core. Based on this configuration, the appropriate factory is instantiated and registered using Dependency Injection. The rest of the application interacts only with the abstract factory and interfaces, without knowing the concrete implementation details. For example, a repository class that performs data operations simply calls factory.createConnection and executes queries without worrying about whether it is using SQL Server or MySQL. This approach ensures that all database-related objects used in a single operation belong to the same family and are fully compatible. It eliminates the risk of mixing objects from different providers, which could lead to runtime errors. It also keeps the code clean and free from complex conditional logic like if-else or switch statements scattered across the application. Another key benefit in .NET is seamless integration with Dependency Injection (DI). The abstract factory can be registered as a service, and different implementations can be injected based on environment or configuration. This makes the application highly flexible and easy to extend. For example, if a new database like Oracle needs to be supported, developers only need to create a new Oracle factory and corresponding classes, without modifying existing business logic. Additionally, this pattern improves testability. During unit testing, developers can inject mock factories that simulate database behavior, allowing the extensible and future-proof. Additionally, this pattern improves maintainability and testability. Since object creation is centralized, any changes to UI component creation logic can be handled within the factory classes. Developers can also easily test the application by substituting mock factories that simulate different platforms. In summary, the abstract factory pattern provides a powerful and practical solution for building cross-platform UI applications. It ensures consistency, reduces complexity, and allows seamless scalability, making it an essential design pattern for modern software development. The abstract factory design pattern offers several powerful advantages in .NET applications, especially when dealing with complex systems that require the creation of multiple related objects. One of the most significant advantages is consistency across object families. In .NET applications such as database providers, UI frameworks, or service integrations, multiple components must work together seamlessly. The abstract factory ensures that all objects created belong to the same family and are fully compatible with each other. For example, when working with a specific database provider like SQL Server, the factory guarantees that the connection, command, and transaction objects are all aligned, eliminating the risk of runtime errors caused by mixing incompatible components. Another major advantage is loose coupling, which is a core principle in modern .NET architecture. By depending on interfaces rather than concrete classes, the client code becomes independent of specific implementations. This makes the system more flexible and easier to maintain. For instance, in an ASP.NET Core application using Dependency Injection, switching from one database provider to another can be done by simply changing the registered factory without modifying the business logic. This greatly improves the adaptability of the application. The pattern also strongly supports the open/closed principle, allowing developers to introduce new families of objects without altering existing code. In a growing .NET application, this is extremely valuable. For example, if a new database like Oracle or a new external service needs to be integrated, developers can add a new factory and corresponding classes while keeping the existing system untouched. This reduces the risk of introducing bugs and makes the codebase more stable over time. Another important benefit is centralized object creation. In .NET projects, especially large enterprise systems, object creation logic can become scattered and repetitive. The abstract factory consolidates this logic into a single place, improving code organization and readability. It also makes it easier to manage changes, as developers only need to update the factory rather than multiple parts of the application. Additionally, the pattern enhances testability. Since the application relies on abstractions, developers can easily inject mock factories or stub implementations during unit testing. This allows testing of business logic independently of actual external dependencies like databases or third-party services, leading to more reliable and maintainable code. However, despite these advantages, the abstract factory pattern also has some drawbacks. One of the primary disadvantages is increased complexity. Implementing this pattern requires multiple interfaces, concrete classes, and factory classes, which can make the code base larger and more difficult to understand, especially for beginners. In small or simple applications, this level of abstraction may be unnecessary and can lead to over-engineering. Another limitation is that adding new product types can be difficult. While the pattern makes it easy to add new families of objects, introducing a new type of product, for example, adding a new method like createReport, requires changes to the abstract factory interface and all its concrete implementations. This can be time-consuming and may violate the open/closed principle in certain scenarios. There is also a higher initial development effort. Designing and implementing the abstract factory structure requires careful planning and a good understanding of the system requirements. This can slow down development in the early stages, although it pays off in the long run for large and scalable systems. In conclusion, the abstract factory pattern in .NET provides strong benefits in terms of consistency, flexibility, scalability, and testability, making it highly suitable for enterprise-level applications. However, it should be used judiciously, as its added complexity and structural overhead may not be justified for smaller or less complex projects. The abstract factory design pattern is a powerful creational pattern that provides a structured way to create families of related or dependent objects without specifying their concrete classes. Instead of instantiating objects directly, the pattern introduces an abstraction layer through factories, ensuring that all created objects belong to the same family and are fully compatible with one another. This makes it particularly useful in complex applications where multiple components must work together consistently, such as UI frameworks, database providers, and enterprise service layers in .NET. One of the key strengths of the abstract factory pattern is its ability to promote loose coupling. The client code depends only on interfaces and abstract factories rather than concrete implementations, which makes the system more flexible and easier to maintain. This abstraction allows developers to switch between different families of objects, such as changing a database provider or UI theme, without modifying the core business logic. As a result, the application becomes more adaptable to changing requirements. The pattern also aligns strongly with the open/closed principle, enabling developers to introduce new families of objects by adding new factory implementations without altering existing code. This enhances scalability and reduces the risk of introducing bugs during system expansion. Additionally, by centralizing object creation logic, the abstract factory improves code organization, readability, and maintainability, which is crucial in large-scale .NET applications. Another important benefit is consistency and reliability. Since all related objects are created through the same factory, there is no risk of mixing incompatible components. This ensures that the system behaves predictably and maintains a uniform structure across different modules. However, the pattern does introduce some complexity, as it requires multiple interfaces and classes. It is most suitable for applications where there is a clear need for managing families of related objects and supporting multiple configurations or environments.